Welcome back for part 6 of the Building Science for Dry Climates video series with Franklin Energy. In this video, we're going to look at mechanical ventilation, why it's so important, and the standards that guide our strategies to meet or exceed the minimum ventilation requirements. Be sure to watch the other videos in the series. They're presented in a way that's meant to help you evaluate a house as a system and inform your approach to deliver affordable, comfortable, and energy-efficient homes to your customers. Let's dive into mechanical ventilation. When you really look at the way we've built homes for the last 100 years, you can see the changes in styles, from balloon framing in the early 1900s to the shift to platform framing around the end of World War II, the change from lath and plaster to drywall finish, even the emergence of plywood as a way to provide shear strength. Keep looking, and you'll see the shift in the late 70s to include energy efficiency in the building code, and again in the early 2000s with air sealing and duct sealing requirements. For many of the previous decades, our housing stock was built in a manner that provided a safe shelter, but wasn't particularly energy efficient. In today's world of new construction, as well as energy efficiency retrofits, we're air sealing our homes to new levels of air tightness. And it's become increasingly important to look at mechanical ventilation as the way to ensure healthy indoor air quality, to minimize the buildup of carbon monoxide, and provide adequate combustion ventilation air for our combustion appliances. Ventilation is important because even with normal occupant behaviors, we can see the buildup of indoor air contaminants like carbon monoxide from our combustion appliances, volatile organic compounds from paints and solvents, things like carpet, and relative humidity and water vapor that can lead to condensation, mold, and other moisture-related problems. While older homes were leaky enough to provide the natural air infiltration that let these contaminants out or dilute themselves, we've learned that we can save a lot of energy by air sealing those air leaks and keeping our conditioned air in. By keeping the cold air out and our warm air in the winter, we can save hundreds of dollars on utility bills. This new level of air tightness requires a purposeful strategy to get the stale indoor out, some clean, fresh air in, and if possible, uses a pressure neutral strategy that minimizes positive or negative house pressures that in turn could drive unwanted infiltration or exfiltration of the air through the building shell. So we already try this with exhaust fans, but it's crucial to do it right. If the goal is to get the moist air out, you got to get it all the way out. This kind of poor craftsmanship is just going to dump warm, moist air into the attic, which can lead to serious moisture problems. One of the mantras of the building science community is to seal tight and ventilate right. Let's look at some ventilation strategies. We could leave the homes leaky so they don't get those contaminants built up, right? Nah, we moved away from those codes and standards that allowed for shell leakage to provide the minimum ventilation requirements. We can use whole house exhaust ventilation systems, or even better, we can use heat recovery ventilation systems, which capture outgoing exhaust air temperatures and precondition incoming fresh air, transferring the heat in the desired direction, while continue to use spot source ventilation, like bathroom and kitchen exhaust fans, to get moisture and other contaminants out. We're going to use terms like minimum ventilation rates to describe what houses need to maintain good indoor air quality. We're going to talk about the ASHRAE 62.2 ventilation standards to meet those mechanical ventilation requirements. We're going to describe air movement in terms of cubic feet per minute and how that affects a home's total leakage or ventilation needs by looking at a home's air changes per hour. And we have looked in other videos at using a blower door to measure shell leakage and the N factor is that key to translating a blower door test result into an actual measurement of a home's natural leakage rate. So let's look at the two most commonly used ASHRAE ventilation standards. We use ASHRAE 62.2 from the year 2010 when we're looking at describing strategies for existing homes, where the ASHRAE 62.2 standard from 2013 is more commonly applied to new homes for Title 24 compliance. It's also the adopted standard for existing home requirements in the popular BPI standards and protocols. Both standards use an occupant load consideration of 7.5 cubic feet per person, part of the formula, and both standards use the size of the house as the other piece. But the 2010 standard requires only 1 CFM per 100 square feet, and the 2013 standard requires 3 CFM per 100 square feet. Let's look at how that plays out so you can see how the ventilation requirement can be applied. We're trying to determine the amount of air that the mechanical fans have to move. So with the ASHRAE 2010 standard, you can multiply the square footage of the home by 0.01 to get the 1 CFM per 100 square feet part of the formula. And you could take the number of bedrooms and add 1, assuming that there are 2 people in the master bedroom, and multiply that by 7.5 to get the CFM required for the occupant load. Adding these two together will give you your total minimum ventilation rate that's required for the home. It can be continuously running fan, or in some cases can be intermittently running, but it has to be from fresh air outside. Let's look at a 4-bedroom house that's 1,000 square feet. And with 2 people in the master bedroom, the occupant load would be 5, and 5 times 7.5 is 37.5. And with 1 CFM per 100 square feet, 1,000 divided by 100 gives us the extra 10 CFM. And together, when you add them up for that house, you see the need 47.5 CFM. In some jurisdictions, they allow you to count existing ventilation credit towards your required minimum ventilation rate. And for this example, 20 CFM is used. So the remaining 27.5 CFM is what must be provided by additional mechanical ventilation. Tables like this exist for the 2010 ASHRAE standard that can help you skip the math and just meet the requirements based on the table. Notice in this table, a 4-bedroom, 1,000 square foot home needs 48 CFM, which would cover the 47.5 requirement that we just came up with in the previous example. With the 2013 ASHRAE standard, the formula is very similar. 7.5 CFM per occupant is the same, but the 2013 formula requires 3 CFM per 100 square feet. So you still take the number of bedrooms and add 1, assuming that there's 2 people, and multiply that by 7.5. Jump right into this slide. 37.5 CFM is still the requirement, but with 3 CFM per 100 square feet, there's 30 CFM addition. When you add those together, you get 67.5 mechanical ventilation required. And if your jurisdiction does allow you to use that ventilation credit, we can still use the 20 for existing ventilation, and the result would be 47.5 CFM is the target of remaining mechanical ventilation that you need to install. This table for the 2013 ASHRAE standards exists as well, and you can see that on this table, a 4-bedroom, 1,000 square foot required 68 CFM, which just exceeds the 67.5 that we came up with this most previous slide. Tables take the highest number required for the largest home in that size range and just make it an easy reference for us to use out in the field. So which standard should you use? Well, you should know them both and use the 2013 standard for the work scope proposals. And you should install continuous mechanical ventilation to meet the higher rate or the one that meets the code in your local jurisdiction. Even when perfectly designed and installed, fans may not perform at their rated CFM because of static pressure. Static pressure is the resistance from the inlet grill, the duct runs, elbows, and outside terminations that the fan must overcome to move air through the system. Factors affecting static pressure include the length of material, the type of ducts you're using, how many bends and kinks or elbows air has to flow through along the way, the types of grills or register the air is moving through, and the end caps, maybe where the air is being exhausted outside. Even things like filters all add up to increased static pressure. Air flows more easily through smooth materials than rough. Air flows more easily through this than this or this. Determining the equivalent duct length is one way to account for static pressure when sizing fans. All manufacturers have performance curves for the fans they manufacture. They all provide tables to determine the actual fan size needed to overcome static losses and reach the CFM requirements. Let's take a bathroom example where we converted the ACH requirements to cubic feet per minute when the target was 8 air changes per hour. That requires 90 CFM. Assuming we're using 12 feet of 4-inch flexible aluminum ductwork with one 90-degree elbow and an end cap, the equivalent duct length is actually going to be 60 feet. Here's how. The duct material, flexible aluminum, offers more air resistance than rigid, smooth metal ducts. So we multiply the length of the duct, 12 feet, by the factor of 1.25 to account for increased resistance. 12.125 is, again, 15 feet of equivalent duct length. Pushing or pulling air through a 90-degree bend is harder than through straight ductwork. So in this case, it's difficult as pushing or pulling air through 15 more feet of straight ducts. And the end cap creates as much resistance as moving air through another 30 feet of straight ducts. The result shows us that adding 15 feet for the resistance, 15 more feet for the elbow, and 30 feet for the end cap, 60-foot equivalent duct length for that 12-foot length of flex that actually got installed. Use the fan sizing chart from the manufacturer to determine which fan achieves the goal of 8 air changes per hour through 60 feet of equivalent duct length. Based on the calculation in the last slide, a fan that can move 90 CFM is required. This table indicates that to overcome the static pressure and achieve those 8 air changes per hour in a 90 square foot room with 60 feet of equivalent duct length, that the 1.5 VQ3, which is a 150 CFM fan, would be required. Here are some basic guidelines to follow when you're installing the ductwork for your mechanical ventilation system. Make sure the exhaust gets all the way outside. Use short, straight, well-sealed ducts. Try to get 2 or 3 feet of straight pipe before your first elbow. Use long radius elbows. Use smooth materials. Insulate ducts in the unconditioned spaces. And make sure the termination cap can keep critters out. Follow manufacturer's specifications and installation instructions. This hood fan has the properly sized duct. It's smooth and straight, flows directly outside. Use short, straight, well-sealed ducts. Use 2 or 3 feet of straight pipe before the first bend. This helps the air get up some speed before it meets the resistance of going through the elbow. Use long radius elbows when possible and avoid tight kinks coming right out of a fan housing. Use smooth, rigid ducting when possible. Insulate ducts running through unconditioned spaces. Insulation will reduce condensation and conserve energy. Grills at the termination keep animals out, which is safer for them and better for your home. Dryer vents and the ducting we use follow a lot of the same guidelines as other mechanical system ducting. Use smooth materials, short, straight runs of vent go directly outside. Also use smooth, tight connections. Insulate dryer ducts in unconditioned spaces, and exhaust terminations should prevent leaks as well as pests. Some additional things to remember with dryer vents include the lint and warm humid air that's being exhausted. Wherever duct materials are connected, remember that the inside of the pipes must allow smooth airflow. No screws. Screws can collect lint as it blows past and eventually lead to blocked vent, fire, or both. Connect vents with HVAC foil tape, not duct tape. Duct tape can't tolerate the extreme conditions and will fall apart every time. Once these ducts on the left are insulated, they'll be perfect. Smoother and straighter are better. Rougher materials cause lint buildup. Lint buildup can lead to reduced dryer performance, which wastes energy. It can also lead to fire. According to the Consumer Product Safety Commission, there are over 13,000 home fires each year caused by dryer vents with buildup of lint or debris. The exterior termination for dryer vents needs to allow for the flow of the exhaust, needs to prevent air and water from leaking back into the home, and keep pests out. Dryer vents should not have unnecessary bends, definitely should not ventilate inside of the home or crawl space, and should not be made with plastic pipe or contain leaks or allow lint to build up. What do you think happens in the winter when warm, humid air passes through this plastic flex duct in a cold, unconditioned crawl space? That's right. The moisture condenses inside the ducts. Lint gets bogged down in the moisture and ducts get clogged. Over 3 gallons of water will drain from these hoses. It's a pretty dramatic picture that helps to drive home the points that we've been discussing. In conclusion, it's important to remember that tighter homes need to maintain proper ventilation strategies to maintain healthy indoor air quality and adequate combustion air. And that while previous ASHRAE standards allowed for some minimum shell leakage to provide the minimum airflow needs, leaving homes leaky is no longer a ventilation strategy. We have to provide the required minimum ventilation rate with a mechanical ventilation system. Use appropriate ASHRAE guidelines to determine the required CFM needs. Consider static pressure when sizing and installing the fans. Install the ducts properly. And lastly, when installing dryer vents, remember that dryer vents and ventilation ducts share characteristics regarding airflow, but you should be extra conscientious about how to avoid lint buildup and condensation issues. Thank you, and be sure to watch the other videos in the Building Science for Dry Climates video series.